Section 4.3, we're continuing our discussion of linear and nonlinear, except in the context of inequalities now. And we're going to reduce the discussion to two variables so that we can graph these in our calculators and look at the solutions. Okay, so as always, we start out with the definition that sort of nails down the general form of the equation, or in this case inequality, that we're dealing with. And it's linear, so again we have exponents of our x and y variable, two variables, so there's only an x and a y. There is no z as in the last section, but each variable can have its own coefficient, and then c is our constant, and these are inequalities, and so you get to place your favorite inequality symbol in between the two. So we could have other forms like ax plus by greater than c. We could have ax plus by less than or equal to c, and then we can have ax plus by greater than or equal to c. So these are our four inequality symbols. Less than, or equal to, is greater than, or is greater than or equal to. Alright, any function that cannot be placed in the form of ax plus by is nonlinear. So in example 1, what we want to do is identify the linear ones versus the nonlinear ones. So a, if you check the exponents of the variables, they are 1, and x and y are not located in the denominator. Okay, there's no fraction where x and y is on the bottom, so this is linear. And b, once again, x and y, exponents 1, and so it's linear. But then we get to c, and we see we have an exponent of 2 for the x variable. This is nonlinear. And the same for d. It's just that now the x and the y have an exponent other than 1, 2 and 2. So this is a nonlinear system. Here we could look at this. We don't have a y, but that's okay. It could be written in the form of negative 2x plus a 0 times y. The coefficient of the y is 0, less than or equal to negative 3. Alright, so in this case we only have one variable left, with 0 being the coefficient of y. And if you were to graph it, it would be a straight line. The exponent of x is 1, so this is linear. And so is 4y greater than or equal to 2. The exponent of the y is 1. And this would be a horizontal line, and this one would be a vertical line. So vertical and horizontal. But we could label it as a linear inequality. Alright, so for a solution, we're looking for a number for x and y, an ordered pair that satisfies the inequality. And there's an infinite amount of xy pairs, and these pairs are they don't necessarily have to be on the line. In some cases they're not on the line that we graph, They can be below it or above it. Okay, so these solutions are usually an area that we shade on the XY plane. So in example 2, it says we want to graph the inequality 1b and show, well, we want to first show that this ordered pair 1, negative 3 is not a solution, but 1, 2 is, and then we graph it on this XY plane over to the right. So let's see, 1b is a negative 2x plus 4y greater than a negative 8. Okay, to check the ordered pair 1, negative 3, we read the ordered pair as x being 1 and y being a negative 3, and we replace the variables in the inequality with these numbers: 1 for x, negative 3 for y, and we want this quantity on the left to be greater than negative 8. Well, we get a negative 2, we get a negative 2 minus 12, and that gives us a negative 14 greater than negative 8, and that's not true. If you were to write out a number line, negative numbers on the left, positive on the right, and you were to start at 0, then we would get to 1, 2, 3, 4, 5, 6, 7, 8. We'd get to the negative 8 first. And so that means that negative 8 is farther to the right than negative 14. So negative 8 is actually greater than the negative 14. So this is not true. And therefore 1, negative 3 ordered pair is not a solution. Our second ordered pair, 1, 2, if we follow the same procedure, we write negative 2 times 1 plus 4 times 2. Is that greater than negative 8? Alright, we get a negative 2, and then we get an 8. Negative 2 and 8 give me 6, and yes, a positive number is always bigger than a negative number, so 6 is greater than negative 8. So the point 1, 2 represents a solution to the inequality. So how do we show this graphically? Alright, what we want to do is sort of put it in slope-intercept form. Or in other words, we want to get the y by itself. And so we write plus 2x on each side. 2x cancels. We're left with 4y is greater than 2x minus 8. And now to finally get the y by itself, we divide both sides by 4. And we have y is greater than 1/2 x, which is our slope, 1/2, and then our y-intercept 2. So we're just going to graph this as we normally would, locate the y-intercept, and then apply the slope. However, y is not equal to this line. It's greater than, and so to graph this, we're going to use graph using a dashed line, because we do not have one of the inequalities that has an equal to bar on the bottom. So for -2, we are located right here, and if I go up 1 and over 2, that will put me at +2, where +2 is our x coordinate and -1 would be our y. And then if we repeat the up 1 over 2 procedure, we land at our next point along the line for 0. And so normally we put a solid line, but in this case we're going to put a dashed one. And I could probably make that a little more straight in the middle. Alright, so why is it dashed? Well, y is greater than these points that fall along this line. They are not equal to the points. Okay, where are the points greater? Where is y greater than this line? All up above here. Okay, so we could just shade this region up above the dashed line. Okay, if you had gotten confused about which area to shade, the top or the bottom, then what you could do is fall back on the two ordered pairs that we were given in the beginning. We actually tested the point 1, 2, and the point 1, 2 is located right there. The other one that we tested was 1 and -3, which would be located right about there. So we have a positive y, and then we have a negative y along x equal 1. This one worked and this one didn't, and so that alone should tell you that the upper part above our dashed line is the area that we want to shade. Any of these points that we find up here in this region would be an ordered pair, because it's a point on the xy plane. It would have an x and a y, and those numbers would satisfy this original inequality. Okay, so we basically, to solve that problem graphically, we basically followed 3 steps. We could have replaced the inequality sign with the equal sign and sketched the line. It's going to divide the xy plane into 2 regions. In the previous example, we had an upper division and a lower one. Then what you want to do is choose arbitrary points from one of the 2 regions and test them, okay, to check and see which one's going to be a solution and which one isn't. And then in the area where you pulled the test point from that actually is a solution, you shade that region. Okay, that region would represent our solution set. Okay. Now, if you have a less than equal to or greater than equal to, you use a solid line. If you have a less than or greater than symbol, you use a dotted line or a dashed line, either one. Alright, so let's work another example. Example 3, we have this inequality, and what we'll do is we'll follow the steps from above. We didn't do this in the first example, but temporarily we'll replace the inequality with an equal to sign, and we'll put this equation in slope-intercept form. In other words, we get the y variable by itself on one side, okay, and so at this point what we do is we locate the y-intercept and the slope. We put a point, we plot a point on the y-axis at 3. Okay, that's what a y-intercept is. It's the point that this line crosses the y-axis. So we place a point there for the y-intercept, and then the slope just gives us directions to follow to get to a second point on the line. So we have the slope -3 over 1, and this tells us how much to rise versus how much to run. Rise is vertical, run's horizontal. For the rise, negative means that we go down, positive means we go up, and for the run, plus means we go to the right, and negative means we go to the left. So to translate these instructions, we would say down 3 and right 1. Down 3, right 1. So if we go down 3, we go 2, 1, 0, and then we go right 1, and we land at the point 1, 0. And from here we follow the instructions again. From this second point that we found, we go down 3, which would take us to a -3, and then we go over 1, which would take us to a +2, and our point falls somewhere around in there. What kind of inequality symbol did we start with? That is going to determine what type of line I sketch here. Is it dashed or is it solid? With the equal to part, that tells us that we use a solid line. So I can just connect these the way we usually do. And I try to draw this as straight as I can. Alright, so a solid line, probably do a much better job with a ruler, but there's our line, and now what we want to do is find some test points. Okay, we just want to pick any point, one in this right region and then one in the left. So it sort of depends on how you look at it. You could look at this as the right side or the left side, or maybe you could look at this as up and the down. Doesn't really matter. You just want to pick easy points in both areas. Okay, one side of the line, the other side. These are easy points because y equals 0, so the coordinates to this point are 2, 0, and this one is the origin, so it's 0, 0. Alright, so we go back to our original inequality. And I plug in these coordinates. And we're looking, we only really have to do one, because if one works, then it's the solution. If it doesn't work, then the other one's the solution. So for 0, 0, y is 0, x is 0, 3 times 0 is 0, 0 plus 0 is 0, and this one checks out. 0 is less than 3, and so this would be the region that we would shade. Okay, if you want to, you can go ahead and just check the other ones, but you'll see that they don't work. 3 times 2 plus 0 less than equal to 3. we get 6 is less than or equal to 3, which is not true. 6 is greater than 3. And we've already taken care of the equal to part by drawing a solid line through the coordinates that we found. And that's all there is to it. So we'll move on to our next example. This one is nonlinear, but the same principle applies. Just replace the inequality with an equal to sign and graph it in the usual way, and then pick a point on one side of the line and then pick a point on the other side. Whenever we graph things, we usually orient it to where the y is by itself. And doing that with this expression, we get negative x squared plus 1. We don't want a positive, we don't want a negative y, so if I change the sign of the y, then I just simply run through the rest of the equation changing the other signs. So this would become an x squared minus 1, and this is just a standard parabola shifted down 1 unit on the y-axis. So we would start our parabola right about here, and then if I put in x equals 1, then I'd get 1 squared minus 1, which would give me this point, 1, 0. And then the same on the left side. If I put in a negative 1 and square it, once again I would get 1 minus 1, which is 0. So we fall on the x-axis right here at x equal negative 1. So it's a parabola. It's U-shaped. Looks something like that. And what we want to do is pick 2 points. In this case, one of our favorite points is the origin, and it actually falls on this upper inside region. So one of our points will be 0, 0. And then let's see, we want to pick another point, y-axis, or really wherever, but I guess if you picked the point on the x or the y-axis, you'd at least get 1, 0. And if I pick this one, x is 0 and my y is negative 2. So I've got a point on either side of the line that we just graphed. And now what I want to do is go back and plug in each one of these ordered pairs separately and see which one actually works. With x being 0, we get 0 squared minus y, and y 0 also. Is that less than 1? Well, this whole left side becomes a 0, and 0 is less than 1. So we would shade the side with the origin on it, because the origin satisfied the original inequality. Okay. That's kind of creepy. But anyway, we shade this area, and one last thing you want to check, which I just sort of blew over, is the inequality has an equal to part to it, a dash on the bottom, and so that indicates that we would put a solid line, we would graph our equation with a solid line. Okay, and that's exactly what I did. And that's all there is to this particular one. Of course, you could go back and test this point, but it's not going to work. We get 0 squared minus a minus 2. And this isn't true. 2 is actually greater than 1. It's not less than or equal to. Next one. So that we don't confuse ourselves, we can just temporarily replace the inequality with an equal sign. If I get the y variable by itself, which is usually how we graph things, we get negative 4y equals negative 3x plus 12. And now we run through the equation and divide everything by negative 4 so that y will finally be by itself. A negative 3 over a negative 4 is just a positive 3 over 4. This is our slope. And then 4 divided by negative 4, or I'm sorry, 12 divided by negative 4 is a negative 3. The lone number by itself is where our line crosses the y-axis. So I go down, let's see, how many units is 1, because I want to go 1 below this negative 2 for a negative 3. We have 1, 2, 3, oh, it looks like a different scale. No, 1, 2, 3, 4, 5. Alright, so I want to go 2.5 for 1, so 1, 2, and here we are 1 below negative 2, which is negative 3. That dot is the result of this negative 3. Now we apply our slope of 3/4, meaning we go up 3 from here and over 4. So I'd go 1, 2, 3, and I'm here temporarily, and then I go to the right 4. Both the rise and run are positive, so that would be up and to the right. 1, 2, 3, 4. And that point is the result of starting with the first point and applying the slope. Up 3 over 4. Alright. So now, what we do is we look back at our inequality symbol and we decide what kind of line are we actually going to use to connect the dots. And with the greater than inequality, with no equal to dash on the bottom, we use a dashed line. Or if you want 2 dots, doesn't make me any difference. Now, we pick points on either side. Origin's on the top, so I'll check that one. And that's really the only one that we have to check. Go back to the original inequality, not the equation. I just used the equation so that I could graph this dashed line. 0 for x and y. Is that greater than 12? Well, no. It's going to zero out both of these terms, and we get 0 is greater than 12, which is not true. So 0, 0 is not located in the region where our solutions lie. Our solutions are down below the line. Okay. If you wanted to, you could test a point. Let's say this is 0, negative 3, so we want to go below that and test 0, negative 4, and we get 3 times 0 minus 4 times a negative 4 greater than 12. This 3 gets knocked out by the 0, and minus minus would give us a positive 16, which is greater than 12. So once again, just sort of a confirmation that we shade this bottom region. Okay, when you have an equation where the only variable in the equation is y, and what you have is a horizontal line. If you only have x, then you have a vertical line. So only y horizontal tool, and only x vertical. And we're talking strictly in the case of linear inequalities or linear equations? Well, it's the same drill here. We want to get the variable by itself, whether it's x or y, and in this case, since we have y, we divide both sides by 3, and we have y is greater than negative 4 over 3. To put this in the equation format, we just temporarily replace the inequality with an equal sign, and so regardless of what the x is, notice how this equation does not have an x in it, so it doesn't matter what the x is. Y is just always negative 4, 3. So if you're at x equals 0, you go up, well actually you go down because y is negative, and this is approximately negative 1.3. So we go down a little ways past negative 1, and we put a dot. Well, what if x is negative 2? Well, it doesn't depend. This equation doesn't depend on x. So once again, I would go down to negative 1.3. Everywhere along the x-axis, y equals negative 1.3. Okay, we want to connect these with the line, and this one's a little bit, these are a little bit below that one, but this should form a flat line, horizontal. What kind of line do we use, solid or dashed? Inequality with no equal to bar below it means that we use a dashed line to connect these coordinates. Okay, and now we want to test the points above it, below it. Our favorite point, the origin, 0, 0. We go back to the original inequality. This only depends on y, so I plug in the y coordinate, 0. Is 0 greater than a negative 4? Well, no it's not. Okay, it's the other way around, and so that means we shade this region below the line. And we're done. Alright, so now that we know how to graph one inequality and its solutions, we're going to make it harder. That's what college algebra is all about. So we throw in an extra inequality. But we follow the same procedure with each one individually, and then in the end, when we pick our 2 points, we just have to make sure it satisfies both inequalities. So let's get started. We have our first inequality. We take it and replace the inequality with an equal sign. It's linear, so it's pretty simple to graph. But we want to rearrange it to where y is by itself. So we move the x, we subtract it from both sides. We have a 2y, so we divide by 2. And we get y equals negative, and we could write this as a negative half times x, and then plus 7 over 2 in decimal form is 3.5. This gives us a better idea as to where our y-intercept is going to fall. We have a less than equal to sign for the inequality, and so this means a solid line for the first one. So let's find our y-intercept. It is right about there, 3.5 positive, And now with our slope of -1/2, we want to go down 1 and right 2. So down 1 will get us to y equal 2, and then right 2 will get us to x equal 2. There's our point. So if the slope is negative, you want to go from left to right. You want to be pointed in the downward direction. Okay. Negative slope, left to right, you go down from left to right. Alright, solid line. We only need 2 points on a line to graph it, and so it's going to end up looking something like that. So we've completed the first one. We don't want to shade anything yet because we need to consider the second line that we get along with the first one that we just graphed. So let me erase all of this stuff, and we'll do the same for the second inequality. We replace the inequality symbol with the equal sign, and we graph this line. To get the y by itself, we first have to subtract 5x from each side, and we want our y to be positive, so now we change the sign of all of the terms in the equation, and we get 5x positive and -2. This one has a y-intercept of -2, which is located right there, and with a slope of 5, we have a rise over run of 5/1, and so this means we go up 5 and right 1. So we start at -2, we go 1, 2, 3, 4, 5, and so temporarily we're right here on this dot, our first line, but now we still have to go right 1, and so we would be right about here in line with x equal 1 and y equal 4. 2 points is all you need to graph a line, and once again we have greater than and equal to. So with an equal to symbol below the inequality, we have a solid line. So I connect these 2 points with a solid line as best I can. And now we're to the point where we want to test these regions, and we have 4 regions now instead of 2. Alright, here's our favorite point, 0, 0. So does it work for the first one? Well, we get 0 plus 2 times 0 less than 7. The 0 knocks out the 2, plus another 0 gives us this inequality, and this is true. But we don't shade just yet. We need to check 0, 0 for the second inequality as well. And it's not going to work for this one. The 0 knocks out the 5. Minus 0 would just be 0. But 0 is not greater than 2. So we do not shade this region, and we have to guess again. We have to pick a second point to test. So this one did not work. Another point. 1 in one of the other 3 regions. I'll pick this one. 2, 0. X is 2, y is 0. 0 knocks out this 2, and we get 2 is less than or equal to 7, and that's true. And so now we'll check it for the second inequality, and we're going to get lucky. We have 5 times 2 is 10, minus 0 is greater than or equal to 2, 10 is greater than 2. Check. And so now we shade this region. Alright, and you could test the other two, but they're not going to work out. And one thing you definitely want to be aware of is the accuracy at which you drew your lines. Okay, and if you're in doubt about where this line actually crosses the x-axis, I suggest you pick a point far away from the line. So I'll pick 8, 0. Alright, so this is the point for this upper right hand region, and if we test the points, we get 8 plus 2 times 0 is less than or equal to 7. We get 8 is less than or equal to 7, which is not true. So it doesn't work for this one. This upper region is not a solution. And we'll pick a point for the last region, 0, 6. If I use 0 and 6 for x and y, I get 0 plus 2 times 6 less than or equal to 7, which is not true. So this region, neither one of these are solutions. Now, if you were to have picked 6, 0, it would have worked, and you may have been tempted to shade this region, but that's because we didn't draw this line very accurately. Okay, this line actually has an x-intercept that equals 7. Okay, this particular line came from, let's see, the first one. And if you want to find the x-intercept, you replace y with 0. And if we also replace the inequality with an equal sign, then we get our x-intercept equals 7. So this line should have passed through here. Okay, not way over here. I dropped down too low when I graphed my line. So again, to avoid this mistake, I suggest you pick points that are way that are far enough away from your line so that you don't make a mistake. Alright, this one we have 4 inequalities, but these second two are really simple. These are just the x and y axis. So if x is equal to 0, we get the y-axis. If y is equal to 0, we get the x-axis. So we'll just go ahead and graph these. And then we'll graph a line along the x-axis. And if the coordinate, if your x-coordinate is greater than 0, then we want to shade to the right of the y-axis. If your y-coordinate is greater than 0, then we want to shade up above the x-axis. So we're going to have a region that's shaded over here in the first quadrant, the upper right. And so we take our first and second inequalities and we graph them. get the y by itself. We divide by 4. We have a negative slope, so this line is going to go down to the right. From left to right, it goes down. We have a y-intercept of 15, and we go down 3, 1, 2, 3, and over 4, and our x-axis is a little bit tricky because we have 2, 4, 6, 8, 10. Each tick mark on the x-axis represents 2 units, and so when we go over to the right on our x-axis, we only go over 2 tick marks. So 1, 2, 3, different scale on the x and y, and then we want to plot a point here at x equals 4. And what we'll do, see, these points are really close together, and so there's a tendency to draw the line straight through these 2 points and then veer off as you either up or down as you go to the bottom. One thing that we can do that would save us is if we found the x-intercept of this line that we're trying to graph. If we found a point really far away from this first point. So to find the x-intercept, you just simply replace the y with a 0 and solve for x. Alright, doing that would give me, let's see, x equals a negative 60 over a negative 3, which would end up being 20. So what I can do is go over here on the x-axis and put a 20. And these points on the x and y axis are going to be important, so we want to make sure this is accurate. So I suggest you do this for each of the lines. Go ahead and find the x-intercept. It doesn't really add too much more work to the problem. And now we'll do the second inequality. Put an equal to sign there so that we don't get confused with the inequality. We get the y by itself, and to speed things along, we would get a negative 1 over 3 x plus 10. So we have a y-intercept of 10, and then we go down 1 and over 3, which would almost be, let's see, all the way to the 4. So down 1 and over 3 falls right about here. Okay, but once again, these points are really close together, so the slope may not be the best route to go. Again, we would get a much more accurate graph if we were to find the x-intercept. Set y equal to 0 and solve for x. So that would look like this. We subtract 10 on both sides, so we get a negative 10 equals a negative 1 over 3x. Multiply both sides by 3 and then divide by a negative. We get x equals 30. Alright, so we've got our points spread out here, make it a lot easier to graph. There we have the equal to inequalities for each inequality, less than equal to, less than equal to. So both of these would be graphed with a solid line. So both solid lines. Well, which part of the graph are we supposed to shade? This part, that one, or that one? Alright, so we'll do a test point, and I'll pick one in this inner region here close to the X and Y axis. Alright, a good one would be, let's say, 5 and 5. We can't use our origin because that falls right on top of the X and Y axis. So if we use 5 and 5, we'll test the first inequality. Just replace the X and Y with 5s. We get 15 plus 20 less than 60. 15 plus 20 is 35, and that is less than 60. So that checks out. And so now we have to test the second one. 5, okay, this is our second inequality. This is our first one. 5 plus 3 times 5 less than 30. And make sure that's the number that we have there. Yep, 30. And so we have 5 plus a 15 is 20, and that is less than 30. And so I already had the region shaded, but I'll shade it a little more. You don't really have to overdo it, but we would shade this inner region right here in the corner of the X and Y axis. Not out here anywhere in this space. Alright. Moving on to the last two examples. Here we have, well, we don't have the X and Y axis. Okay, we have three different inequalities. And you can actually call these last two 4 inequalities. This is the equivalent of x is less than or equal to 2 and x is greater than or equal to -2. So in other words, x is in between 2 and -2. And this one is the equivalent of y is less than or equal to 3 and y is greater than or equal to -3. So y is in between these two values, -3 and 3. So to get an idea as to what that looks like, let's say that each, we weren't given numbers on our axes, so I'll just say 1, 2, 3, 4. This is y equal 1, 1, 2, 3, 4. This is x equal 1. So this defines 1 unit from 0 to this mark, defines 1 unit for the x and y axis. So if we go down 4, 2, 3, 4, we'd have a -1. And to the left, 2, 3, 4, another -1. And I need to go to -2 and -3. I think I made them too big. I need to go back and change. I'm okay on the x-axis, but it's too big on the y-axis. So I'll change my units. I'll do every 2 as 1. 1. So down below this would be -1, because for the y, I want to be between 3 and -3. So I want to go up 3. 1, 2, 3. Well, sorry, 1, 2, 3. Alright. So there's y3. Every 2 units is 1. So 2, 2, and then another 2. Here is my -3. Okay. So to graph these, you could call it x equals 2, x equals -2, with only the x variable. These are vertical lines, vertical, and the other 2 are horizontal. y equal 3, y equal negative 3. And so right here at this negative 3 that I found, well, actually we'd use a solid line, because both of them are less than, as far as the inequalities, are less than, equal to, or greater than equal to. They all have the equal to bar. Try to draw this as flat as I can. Probably didn't draw this one long enough. Alright, and then for the vertical ones, I want to go out to negative 2. 1, 2, 3, 4. Here's negative 2. And I just draw a vertical line. X equal negative 2. This is y equal negative 3. On the right, 1, 2, 3, 4. This is x equals a positive 2. And then my other horizontal line, right there, y equals 3. Alright, so I've sort of boxed myself in here around the origin with this second and third compound inequality. So we've got one that we need to graph. It's not going to be vertical or horizontal. We'll replace the inequality with an equal to sign, solve for the y, which gives us a negative x, and if we graph that, it basically runs from left to right, down through the origin. So the origin is one of our points, and then 1, negative 1 will be another one of our points, and then let's see, 2, negative 2 will be the other one. So it doesn't cross through the corners. Okay, the coordinates of this intersection would be x equal 2 and y equal negative 3. So we don't go through the corners. We cut right through here. Like that. Alright, so we missed the corners. And now what we want to do is look at the inequality. There is an equal to dash, and so we do draw a solid line. And now we want to test points. We either have this lower region or this upper one, but we're definitely inside of the box here. Alright, we know we're in the box, so we don't have to test these bottom two. We just want to test this one. So I will pick the coordinates of this point, and they are 0, 1. Just keep it simple. X is 0, y is 1. Is that greater than 0? Yes, it is. And so that means that this region where the 0, 1 coordinate came from gets shaded. Okay, and so we're done with that one. Alright, here we actually have a nonlinear inequality. This one, the first one, is linear. And so if we go through the routine of replacing the inequality with the equal sign, solving for y, we get negative x plus 1, and so we cross right there on the y-axis, plus 1, and then our slope rise over run, is simply down 1 and up 1. Or, not up 1, but right 1. Okay. Right 1. Okay, run is left and right. So I'm looking at this as a negative 1 divided by a 1, which is the same thing as negative 1. Okay, negative 1 is sitting in front of our x, so that is our slope. So I go down 1 and over 1, and I hit that point right there. So draw a line straight through those points as best I can. So now we do the same for the other inequality. We write x squared minus y equals 2. We solve for the y. Get the y by itself, and we have negative y equals a negative x squared plus 2. And we want the y to be positive, so we just simply go through the equation, changing the signs of the coefficients and the 2. And this is just simply a parabola that usually starts at the origin, but with this negative 2 it moves it down 2 units on the y-axis, and so we land right there. If I go, let's say I go over 1, positive 1. What if x is 1? So what is my y coordinate along this vertical line? If I put in 1 and square it and I subtract 2, I get negative, I get a negative 1. Alright, so I would land right about here. Okay, and if I put in 2, x equal 2, I have 2 squared minus 2. 2 squared is 4, minus 2 equals 2. So I would have the coordinates, let's see, x equals 2 and y equals 2. So my parabola would look like this. And for parabola, it's symmetric, or at least this one is. It's symmetric about the y-axis. And so I just copy what I have here over here on the left side. And repeat the curve for the parabola. I don't think I'm moved over quite enough over here to the right, but that's not really a big deal. We just want to shade the proper region at this point, and so I actually have 1, 2, 3, and then this small corner up here 4. 1, 2, 3, 4, 5 different regions. I'm going to pick the easiest one to test first, and that is 0, 0, the origin, because it falls right in between the line and the parabola. And it's clearly not on one of the lines, so it's an easy test point to pick. So if I test 0, 0 for each of these inequalities, I have 0 plus 0 less than equal to 1. That is true. Check. And now what about 0 squared minus 0? Is that less than 2? 0 squared 0 minus 0, we still get 0. That is true. And so I must have to shade this inner region. Okay, So we basically shaded, if you look at the parabola, with respect to the parabola, you either have the inside or the outside. With respect to the line, you either have the bottom or the top. Well, in this case, we wanted the inside of the parabola and the points inside the parabola that were also below the line, and so that can only be these ones in this region in between the two. So that completes D, and we'll end with an application problem. Okay, the problem reads: a warehouse supervisor is told to ship at least 50 packages of gravel that weighs 55 pounds each, and at least 40 bags of stones that weighs 70 pounds each. The maximum weight capacity of the truck to be used is 7,500 pounds. Find and graph a system of inequalities describing the number of bags of stones and gravel that can be shipped. Okay, so the supervisor has a lower limit, and the weight of the truck has an upper limit. And so how many bags of stone and how many bags of gravel, what are the different combinations that we can ship and get by with these two restrictions? Alright, let's see. We will use X for, because we want to graph it, and it'd be nice if we had X and Y. We'll say X is number of packages of gravel and Y equals the bags of stone. Number bags of stone. Okay, X, as far as the supervisor is concerned, has to be more than 50. X has to be at least 50, so it's either going to be 50 exactly or more, so X is greater than or equal to 50. And then Y, at least 40 bags, so Y is related to 40, and it has to be more than 40 or equal to 40. So here are two of our inequalities. Okay, and now what about the weight? Okay, how do you calculate the weight of the total combination of stone and gravel? Well, we would take the number of bags of gravel, and it said that we have a weight of 55 pounds per bag, so 55 times X would be the weight of the gravel, and then we have stone that weighs 70 pounds each, and so 70 pounds times Y, the number of bags of stone, would equal the total weight, and it said this has to be less than 7,500 pounds. So 55x plus 70y is less than or equal to 7,500. Okay, so to graph this, what we'll do is we'll pull up our calculator. Alright, so I think there's a way that you can put in inequalities, but it's not really necessary. What we'll do is we'll just graph these as lines, and so I'll enter y equals 40, and then we have to rearrange this formula, and what we would get is y equals let's see, 55 over 70 x, and that would be minus, and then we get let's see, minus 7,500 over 70. Actually, that'd be plus. Okay. So we'll pull our calculator back up. And we'll type in minus 55 divided by 70 x and plus 7,500 divided by 70. Enter. And we'll graph it. Okay. We cannot see anything, but if we think about our window limits, then we want x to be greater than 50, and then the y-intercept of this line here is about 100. Okay, it's actually, let's see, we would get a little more than 100. I don't know exactly what it is, but we'll scroll down here to y max and we'll just put in 150. Maybe a little bit less, maybe 120. Okay, and then for x max, we want, all we know is we want x to be greater than 50, so I'll put in 100 for that one too. And so we'll graph it and we'll see what we get. Okay, we'll trace around. I'll just hit the arrow pad and we'll explore our graph. Okay, this is where x is greater than 50. Anywhere to the right we have x greater than 50, and then for y greater than 40 we have this horizontal line here. This is on y equal 40. Alright, so with x equal 50 right about here, we could sort of draw, we could transfer this to our paper, or I can just draw over the top of this calculator and to indicate x equal 50. Alright, and so here's our line. This is our weight limit. Okay, so if we want the bags of stone to be greater than 40, then we want to be above this horizontal line. Okay, so up from here. And then if we want more than 50 bags of gravel, then we want to go to the right of this x equal 40 line, but then we want our limit to stay below this slanted line. And so what we're looking at is this area that looks like a triangle. This inner area right here is the graph of our solution. Okay, and all it wanted us to do is find and graph the inequalities that describe the number of bags of gravel. Okay, we graphed it and we shaded the region where the solutions lie. Okay, in between these three lines. And so that completes section 3, chapter 4. Thanks for watching.